All right, let's do the steady state. Let me just pull up the problem here. All right, so we have, see if this works. No, okay. I need to use my finger. So we have 2NO. Excuse my bad writing. Oh goodness, I'm gonna have to be smaller. Two NO gas to form N2O2. Let's label this as K1. Let's label the reverse as K minus 1. Could be anything. It could be a Ka, Kb. We have H2 gas. N2O2. Gives us water. And pretend I'm writing the state symbols here, like a good chemist. Then we also have N2O. Oops, before I move forward. Let's label this K2, shall we? And we have N2O. Gives us H2. Gas. Gives H2O, excuse me. Plus N2. All right, I'm going to tell you right now. This is a red herring. Because I'm going to label this as slow. Sorry, this is fast. And this is slow. So I'm going to tell you right now this is a red herring. We can completely ignore this step. Forget that exists. So we're down to 2 steps. All right, you tell me. Pause the video and tell me what you think the rate law would be. All right, hope you had enough time to try. So for the rate law, we're looking at the slow step because the rate law is dependent on the slow step. So we have that V0 is equal to K2 H2 N2O2. All right, what's the problem? Look at this. The problem is that N2O2 is an intermediate because it's made in this step and it's used in this step to produce this. So we got to rewrite, we got to get rid of that intermediate because intermediates don't fly when we're making rate laws because they're kind of hard to predict, very high energy, and they're not really around for too long. So we got to get rid of them. All right. Slide 2, let's get it. So what we want to do now, sorry you can't see the Jamboard while I switch to the next slide. Sorry about that. But what we want to do now is use the steady state approximation. So the steady state approximation states that the rate of formation, just say form, is E of the intermediate, which is N2O2, is equal to the rate of consumption of N2O2. And if you want a little bit of a mathematical description of why that's the case, well, what we can do is we can say that the rate of change of N2O2 with respect to time is constant. It's steady. So that's our steady state approximation. And so if we say that the rate of formation, or the rate of change of N2O2, which is the rate of this thing, which is equal to 0, is actually going to be equal to the rate of formation minus the rate of consumption. And then rearranging for the rate of consumption is equal to the rate of formation, we get that. So that's really what we're doing with the steady state approximation, is that we're saying the rate of change with respect to time of N2O2 is equal to 0. And rearranging, if we say that the change of N2O2 with respect to time is the rate of formation minus the rate of consumption, then we can rearrange and say that the rate of formation is equal to the rate of consumption. So next slide. So what is the rate of formation? What is the rate of consumption? Well, going back to the original slide, let's use a different color. I love my colors. stay green, actually. Well, rate of formation is going to be given by that bad boy. Rate of consumption is going to be given by, well, this part right here, because it's going back into NO. And the rate of consumption is also going to be given to this part in K2, because we're using it to make H2O N2. All right, so using that information over here, we have that the rate of formation we said was blue. So the rate of formation was equal to 2NO K1 at 2. Sorry, when we're making rate laws, we forget about the 2. That's my fault here. So we just have K1NO, rate of formation, is equal to the rate of consumption, which is equal to N2O2, the concentration of N2O2, times K minus 1 plus H2N2O2 K2. And again, don't do what I'm doing in your homework. Don't write it on 2 separate lines. Continue the calculation on 1 line to make it nice and easy for your reader to see. All right. Next, always what we want to do in the steady state approximation is isolate for N2O2. So you'll see that N2O2 is common between these 2 terms. Let's factor out an N2O2. So K1NO is equal to N2O2 times, well, what do we have left? We have a K minus 1. And we have an H2, K2. It's an H2. That's a K2. Okay, I'm going to give you some more color, actually. Let's go K1, K minus 1, K2. So that means that N2O2 is going to be equal to let's go K1, let's go K minus 1 plus K2. It's going to be equal to K1 NO over K minus 1 plus K2 H2. Another big part of the steady state approximation is as follows. Because we said that this step is slow. What did we say? Oopsies. Yeah, because we said that this step is slow and this step is fast, we're going to assume that the rate of decomposition of N2O2, or the rate of consumption of N2O2, is much quicker than the rate of formation of N2, of N2O2. Well, we're not really saying that the rate of formation is much quicker than the rate of consumption, because K minus 1 and K2 are both actually rates of consumption. They're both consumption, because as you can see from the first steps here, K minus 1 is N2O2 being consumed to form the reactant, and K2 is N2O2 being consumed to form a product. So what we actually have here is we're just going to forget about what I said. They're both rates of consumption, but because we're saying that K minus 1 is fast and K2 is slow, then we can say that K minus 1 is much greater than K2. Because if K minus 1 is greater, that means the rate of reaction is greater than this rate of reaction. The rate of reaction is really quick, really large. So we can make this assumption because we have that fast and that slow part. Another way we can do that is by saying if we have concentration of reactant, if there's one concentration that is much higher than the other, then we know that that rate is going to be much higher. But I still have to look into that. Let me actually just find that right now. Give me 1 second. Yeah, okay. So what were we saying? Yeah, we're saying that this rate of reaction of K minus 1 is going to be much, much quicker than K2. So that means K minus 1 has to be greater than K2. Because if this process is occurring much more quicker than this process, then we know that the rate of reaction, then we know that the K values has to be much higher to drive up that rate of reaction. is this, K. So if K1 is huge, then we know that it has a faster rate of reaction, which is what we were given in the question. All right, so if K minus 1 is greater, much greater than K2, then that also means that K minus 1 plus K2 is equal to K minus 1. Let's say K minus 1's a million. And K2 is 1. That means a million plus 1 is basically a million. All right, that's something that always tripped me up in high school and college. But there's that. So if K minus 1 plus K2 is just K1. It's just K minus 1, excuse me. And we know that our approximation is just given by this. Let's get a new color. That's ugly. Red. Give enough red. It's just given by K minus 1 NO over K1. Over K1 NO over K minus 1. K1 NO over K minus 1. And then subbing that back into our original expression for rate. We have K times H2 times K1 NO over K minus 1, because we said this was equal to N2O2, which was our pesky intermediate, which we wanted to get rid of. So now we got rid of the N2O2. We're happy. That's gone. And now what we want to do is we want to rewrite this so that we can get rid of the K's. So this is going to be K2, K1 over K minus 1 times H2 NO. And the last part of the steady state approximation, just because we don't like dealing with all of these K's, we want to say that K2, K1 over K minus 1 is equal to K. Let's call that big K. And there's a whole relationship we can get into relating the little k, K1 and K minus 1 to K, to the big K, or the equilibrium K, because we know that K1 over K minus 1 is equal to big K, actually. But that's a story for another day. So anyways, we're getting rid of all these K's. So we're saying that V naught is equal to K times H2 NO. And that's how we use a steady state approximation to derive a rate law. Thanks for